In this video, we're going to do a few examples on conjugate beam method. In this example, we are asked to determine the deflection and slope at point B of the beam shown by the moment area method. So we're given a beam in what you call a cantilever beam, and we're asked to determine our slope and deflection at point B. So now let's project our lines for our shear force, bending moment, and conjugate beam. I'm going to have this one, make them a bit longer. Our conjugate beam is similar to the Morse moment area method on determining our deflection and slope. So we use the same equations for slope, which is area divided by our EI, and deflection, it's area times centroid divided by EI. So now let's find our reaction A, so we can do our shear force and bending moment diagram. Let's use sum of forces R positive is equals to 0. We have RA here going up, and we have moment A going counterclockwise. So we're gonna have our RA minus 90 is equals to 0, and then our RA will be 90 kilonewton. And then for our moment A, we're gonna have sum of moments at A clockwise positive is equals to 0. Then we're gonna have our 90 times 5 minus MA is equals to 0, and our MA is equals to 450 kilonewton meter. Now let's do our shear force diagram. Let's use this green. On our B, we have 90. And then our A, we have the same 90 plus negative 90 plus 90 going back to 0. In structural analysis, you won't be marked for your steps on shear force and bending moment. So the steps are not compulsory, as they were covered in theory of structure, but you will need to show your answers. Then our bending moment at B is gonna be 0, and at A, gonna have our 450, which is 90 times negative 90 times 450, which is negative 90 times 50, which is 450 kilonewton meter, plus our 450 at A, go back to 0. Now let's do our conjugate beam diagram. So with conjugate beam diagram, let's go back to our supports. When you're given a overhanging beam in your real beam, in your conjugate beam, it's gonna change into a inverse support like this. The fixed end is gonna be free, and the free end is gonna be fixed. And then when you're given a an overhanging beam, whether it's a roller or a pin support, they're both going to change into a hinge in conjugate. And when you're given a hinge in your real beam, it's gonna change into a roller in your conjugate beam. What else? Yeah, your simply supported stays the same. So our fixed end is going to be free, and our free end is going to be fixed. And then you have your 450 divided by EI, and then you'll have to show your force lines. You have your A and your B. Now let's go back to the question. Determine the slope and deflection at point B. At point B, our slope at B will be the areas divided by EI. We only have a triangle which is half, our base is 5 times 450 divided by EI. And then you get 1125 divided by EI. Now let's do our conversions. Our E is 200, our I is 800. So we have 1125 times 10 to the 3 divided by 200 times 10 to the 9 times 800 times 10 to the negative 6. And then you get 0.00703 rad. And then for your deflection at B, it's going to be area times centroid divided by EI, which is basically going to be this answer, 1125. Our centroid from here going towards B, it's 2/3 times 2/3 times 5 divided by EI, we get 3750 divided by EI. And then you can, if you are rushing, if you're against time, you can simply not cancel this equation in your calculator and then just add your 2/3 times 5. And then you get 3750 times 10 to the 3 divided by 200. You get 0.0234 meter, which is 23.438 millimeter. Now, when you look at your beam, you know that according to your boundary conditions, your beam is going to bend downwards. So the direction of your deflection is going to be down. Now let's look at a different example. In this example, we're asked to use the same method to determine the slope and deflection at point D, which is here. Let's draw our lines. Let's make them a bit longer. Let's put our shear force. Our bending moment and our conjugate beam. Now let's find our reactions. So you're gonna have your RA and your RC. Let's take our sum of moments at A clockwise positive is equals to 0. We have 155 times 5 minus RC times 10 is equals to 0. RC is equals to minus 155 times 5 divided by minus 10, which is 77.5 kilonewton. Let's do the same for RA. Sum of moments at C clockwise positive is equals to 0. You have RA times 10 minus 155 times 5 is equals to 0. So RA is equals to 155 times 5 divided by 10, which is 77.5 kilonewton. Now, with analysis, it's tricky and risky to use sum of forces when finding your second reaction, because once you get wrong here, you're wrong throughout the whole question. You won't get any marks except for your first reaction. Now let's do our shear force diagram. So RA, let's change color. We're gonna go up to 77 and down to 77 and back. So we're gonna have 77.5 minus 77.5 back to 0. And then your bending moment diagram will look like this, go back down, and then stays at 0. So it's gonna be 77.5 times 5, which is 387.5 kilonewton meter. You can write it down if you want, or you have to write it down because this one is important. The shear force you don't need to write it down, but your bending moment you need to write it down. At A is 0. At B, 77.5 times 5, which is 387.5. At C, it's 387.5 minus 77.5 times 5, which is minus 77.5. And then at D, it's 0. Try to get this right. You know this is 0. Which is equals to 0 and then stays at 0 throughout. Now let's do our conjugate beam. Now our conjugate beam at A is going to stay the same. You're going to have your pin support. At C, you're going to get a hinge, and at D, it's going to be fixed. Give you 387.5 divided by I. Your lines are going up. We have 5 meter, 5 meter, and 5 meter. That's your A, B, C, D. With a hinge, you can separate your beam into two parts. As you'll see, you're gonna have your. Okay, let's draw our forces first, our reactions first. Let's use green. This one is gonna go down because your forces are going up. This side is gonna go down also, but this side is gonna go up. Gonna have your C1 and your C2, which are equal. Your hinge is basically two forces acting in the opposite directions, but they are of equal magnitude, meaning they add up to 0 at the end. So now let's find our reactions. You have your A and your C. Let's find our C first. The sum of moments at A clockwise positive is equals to 0. We'll only focus on the beam, on this beam, this side. So we have the first shape. Now let's put our reaction first. It's going clockwise, so we have your RC1 times 10, and then these ones are going anti-clockwise, minus, let's put the EI outside. You have your first shape, which is 1 over 2 times 5 times 387.5. Now let's open another bracket because these two shapes are equal. You have 5 meter, 5 meter, and they have the same height. So let's do this for your centroids. So you have your first one, which is towards A, it's 2 over 3. 2 over 3 times 5, plus the second one, which is 1 over 3 times 5, plus 5. Is equals to 0. So you have 10 RC1 minus 1 over EI, open bracket, 1 over 2 times 5, 387.5, open big bracket. You have 2 over 3 times 5. You put double brackets here. Plus 1 over 3 times 5 plus 5 bracket. And then you get 9687.5 is equals to 0. And then your RC1 is equals to 9687.5 divided by EI divided by 10, which is 968.75 divided by EI. Now, we don't need to find your RA unless you are asked to find your RA, because now we can focus on this side of the beam. Remember, your RC2 is equals to your RC1. So we have your RC2 and then your RD, will be equal to your RC2 because there's no other force acting on it. And then your MD now let's find our slope at D. Our slope at D will be your area divided by EI, which in this case we only have our reaction. Our area is our force, which is our RC2. We're gonna have our 968.75 divided by EI, which is 968.75 times 10 to the 3 divided by, that's our EI, 70 and 1040. 70 times 10 to the 9 times 1040 times 10 to the minus 6. So divided by 10, get that. So times 10 to the 3, 70 times 10 to the 9, 1040 times 10 to the negative 6. And then you get 0.0133 reds. It's fine. Yeah, that's red. Now let's find our deflection at D, which is equals to the same 968.75 times our distance, which is 5. So if you're 968.75 times 5, and then times the conversion divided by, this is fine, 70 times 10 to the 9, 1040 times 10 to the 6, which you get 0.06654 meters, which is 1000. You get 66.54 millimeters. Now, in a separate video, we'll look at different examples. With we'll look at a UDL example, and we'll see any other tricky examples that we might find. Thank you.